of multi-core processor virtualization features. And our presenters today will be Rajan Goyal, Brian Chin, both from Cavium Networks, and Surender Kumar from Nokia Siemens Networks. And these guys have been leading the effort on a working group inside this consortium to basically try to sort out the confusion of multi-core processor virtualization features. And as you know, there are many processors out there today that include these features, and so it's imperative that we come up with a methodology or a categorization to make it more comprehensible so that system developers can figure out what features they have available and how to use them. And so with that, I will turn it over to our first presenter, Rajan, and he'll begin our discussion.
Thanks, Marcus. Good morning, everybody. My name is Rajan Goyal, and I chair the Virtualization Working Group in Multicore Association, along with Surender. So as Marcus mentioned, we are going to talk about virtualization in the multi-core environment, and how this how this working group facilitate that, and what is our charter and what is our motivation. Okay, great. So I'm gonna so the agenda for this talk is that so next slide. Okay, we are going to I will introduce what is the virtualization, and this webinar is not about virtualization like we are not going to introduce the basics or but how is it evolving, but more about just to set the background about it. And then we will introduce about the working group, what are our charters, and also just to motivate so that we can get you more participation from more members of the group. We are going to share what is our current status, and what are our thoughts and process, and then we'll wrap up with your question and answer. So that's the overall agenda of the talk. Ideally, I would like to keep the discussion interactive, but in this model, you can either keep asking questions while I'm talking. I'll try to get that as a feedback and correct, or at the end of it, we will try to justify our presence here so that we can have more value of our time for next 1 hour. All right, moving along. So just to introduce what is virtualization, or how did it start. So virtualization now, with last 4 or 5 years or more, it has become a more overused word, or you can say nobody is alien to this term right now in the industry, because you can imagine that virtualization is applicable in server market, in processors, in networking, in storage. Every aspect virtualization is being used, and it has been widely adopted in the server-based computing, both for cloud and enterprise, and that has been well understood, and it has been very successful, the use case from business as well as from technical point of view. And along with that, in the industry, there has been migration of virtualization concepts into the embedded computing, mainly to support for legacy operating systems and applications, or another motivation was for isolation and security. And there are many more requirements, because in embedded systems there is variety of IOs, so you need to virtualize them, and it's more fragmented. It's not as standardized as in a standard enterprise or cloud environment, or in the server computing environment. So that all those are the good motivations to do the virtualization. But as many experts in the field have argued so far, in many seminars or conferences, or even in literature, that the virtualization concepts from the server-based computing cannot be applied as it is to the embedded market because of the various reasons. It could be because of the expectations from performance. It could be because of the embedded system development environment, or there are many different reasons why you cannot have just applied those same parameters or same requirements for the virtualization and embedded computing. And that's where this working group comes into picture, meaning within the Multicore Association, this working group is chartered to facilitate the transition in the industry of virtualization from server based computing to embedded market. And we have So that's the background of this working group and the charter for this. Okay. So having said that, what is the a charter for this particular working group? So I'm gonna basically introduce that, but we at the end of it we will have more contact information or details to follow up. We can share more details about the working group charter. But in summary, I'm going to summarize what in nutshell we are being chartered to do that. So we have two charters at high level. One we call software virtualization strategy, and second is called multi-core virtualization profiles. So I'll first talk about what is SVS, or software virtualization strategy. What do we mean by that? So as a background in the industry, before virtualization, the multi-core, you can say, wave was already accepted, and it was coming, and the trend was that NPU, network processors in the networking market, or single core high frequency like from Intel or any other processor vendor, they were being replaced with multi-core. So instead of multi-chip solutions or high frequency solutions, we were having multi-cores, and the idea was to have, general accepted norm was that you run Linux or control plane application on one or a couple of cores or some of the cores out of the full chip, and rest of the cores were used as a data plane, and it could be running another OS, or it could like a real-time OS, or it could be bare metal OS. So that was the you can think of as that is still the standard practice of application software architecture. Now, and it brings, that model was solving the problem because you could use the multi-core to full potential. You could scale with more cores, both in control plane and in the data plane, and it was still a single chip solution. From all practical purposes, it was a very useful and very successful model. But with time, it brought more challenges, like it was more complex to manage, higher development cost, it was very difficult to debug. How do you do bandwidth or resource sharing between two domains, namely control plane and data plane? How do you make sure the bugs in one domain is not making the other domain crash, and so on and so forth? And how do you inter-domain communication between those two domains? So those were all the problems which were coming in, and it was thought of that was the main motivation for virtualization, and virtualization could somehow solve that problem magically or transparently for the rest of the application. So that was the background in the industry, that how virtualization could fit into is one of the architecture where virtualization as a concept or an idea could solve that transition or that problem that was happening in the multi-core, and it could help the adoption of the multi-core more in the networking or embedded market. So that was the first very practical or very more suitable architecture from the industry point of view. But as the development, as the you can think of systems or architectures became more complex, it was bringing more issues than solutions. So what is the new trend happened to be that in the industry is that now everybody wanted to move to a single environment. It could be Linux, FreeBSD, or their own proprietary OS, but instead of two different OSs for control plane and data plane, they wanted to run single OS or single environment. And it should solve, so it has now two contradictory requirements. On one side, it should be flexible so that you could run control plane kind of applications, and on the other side, it has to be low overhead so that you could run your data plane applications which needs higher performance. So those were the two you can say self-competing requirements, but there are many solutions in Linux or FreeBSD where people are trying to solve this problem. But then the question becomes, where does the virtualization fit with this new model? What kind of virtualization is required? And it's a little bit different from the you can think of the previous model of control plane and data plane, different domains and isolation, or resource sharing. It is a little bit different model as compared to that. So that's the number one charter of our working group, is that we want to facilitate the transition to new software paradigm, to the new architecture, and in order to do that, we are going to provide standard virtualization techniques or guidelines. So there is a full set of details that we have worked out, that what we want to work on in terms of some proof of concept that we want to do in Linux or FreeBSD, or some guidelines that how inter-domain communication should happen, or how real-time OS should do a zero copy or between when it is doing I/O, or how do you do I/O multiplexing. All those things are the some of the problems that are showing up in the new environment, and we want to facilitate that transition so that we can help the industry standardizing some of the virtualization techniques and guidelines. So that is the charter number 1. Second charter that we wanted to talk about is the multi-core virtualization profile. So again, just to give you background about what do we mean by that. So one, as I said, is the software aspect of the problem. That is what are the software architecture and how it has been evolving in the industry, and where is the virtualization playing the role. So that is charter number 1. And second charter is that virtualization is not a software only problem. It's a hardware and software problem. It can be software only problem, but it's not very attractive, because then you start losing the performance that you want to get out of the chips. So that becomes detrimental, and in fact people, that would be the that was the challenge number 1 in the industry, and it was slowing the adoption of virtualization, because nobody is willing to give up on performance, or even though you want to have isolation or protection, but not on the cost of performance. So that's why you need an hardware support to keep up the data rates and still do the isolation and protection between different domains running on the multi-core. So that is the well accepted norm. Nobody is denying that. But what is the issue or the problem of the problem statement is that the virtualization hooks as identified by x86 or in the server market are not entirely applicable to embedded SoCs, embedded network processors also. So that's because it's going to different market, and different market segments are networking. It could be mobile infrastructure, data center, or cloud, or any new emerging market, even in storage, where NPUs or multi-core SoCs are being used. So there are different markets, and the requirements are different compared to the server market. And what we do, so you cannot assume that. So question in the from system vendors point of view is, how do you choose the right SoC? That's a problem statement in the industry. What do you compare it with x86 in terms of hardware virtualization hooks, or every vendor has their own claims that everybody claims that they support virtualization, but question is to what extent and for what market. So that's a big confusion or question mark in the industry, and we as a working group wants to again standardize that and clarify that, so that it becomes we don't want to have any it doesn't slow down the adoption of the virtualization in the industry. So this is one of the area that we have identified, so that if we standardize the level of hooks in the hardware, then system vendors can pick the right SoC with the right hooks for their market. So in order to do that, what we have said is that we have agreed as a working group is that we will come up with different grading profiles, or you can call it profiles. There is an example, like you can say basic, intermediate, or advanced, and or level 1, level 2, level 3. These are all we as a working group agree on the high level direction, but in terms of the profiles or things which we are going to talk later in the presentation are still being worked out. And the idea is that working group will generate the detailed specification of different grading and mapping of different features to different grades. So we will come up with that, okay, level 1 for this market should have these features, and level 2 should have these features, and then once we agree, then we are going to grade different SoCs according to different profiles. So that's the overall charter of the working group. Now in digging a little deeper, what it means is that SoC features, that what we realize is can be categorized into different categories. One is that what all hardware hooks are in the core or in the processor and that we call to enable core virtualization. Then another thing is what is about the I/O virtualization, because most of the networking or the embedded SoCs are doing I/Os. So you cannot just do core virtualization. There has to be a lot of hardware hooks for to facilitate I/O virtualization. So that the packets coming in or the commands coming in are directly going to the right VM rather than there is a extra copying involved or any slowdown in that. So there is a lot of hardware hooks required for I/O virtualization. Then third aspect is that all the SoCs in today's market have one or many hardware acceleration. It could be for crypto, for regex, or for storage, or for compression, whatever, depending upon the market segment. There are always hardware accelerators on the SoC. So the question is, how is that virtualized for rest of the VMs? How do the different VMs see those hardware accelerators? Do they have to go through some centralized unit, or is it software virtualized or hardware virtualized? Depending upon the market that SoC is target to, the hardware accelerator virtualization also becomes the critical feature for that. So that's why. So those are the different categories that we are going to split the SoC features into, and then use that for grading of the SoCs. Once we have various profiles, and then what as a group we want to do is that we would get the acceptance from different system companies on one side, like Cisco, Juniper, NSN, and Huawei or other system vendors who are going to be the end user of the SoCs, and also from the processor companies who are the who are going to deliver those and adhere to those profiles. So we will work on both parties so that they agree with the definition that we come up with, the grading, as well as it is acceptable and it is meeting the market demands of the end customers. In this case, those are the system companies who are developing their systems using these SoCs. So that's what the main charter of this working group is, and we are working very diligently to meet that goal. Now, at the end of it, what the objective or the you can say the benefit that we see out of it, that once we achieve this goal, is that all the processor vendors, like it could be Cavium, Broadcom, or LSI, or even x86, or any other vendors who are delivering or who are in this business of SoCs in the embedded market, they can make claim that for this particular chip, our chip, this particular chip is of this profile, right? They will make claim as part of the literature, then that they will say that this is what their chip belongs to, or at this profile. Now, and on the other hand, system vendors will, as part of their RFQ, will ask that, okay, I want to go to this market, and I need just like they say that I need this frequency, this much memory, this many compute or MIPS or whatever, right? In that thing they ask, and similarly they will start emphasizing that I am going to go into storage market, so I need a storage virtualization or this particular virtualization to this profile. I'm just taking an example. So or I'm going to a crypto market and I need a crypto engine virtualized for so many VMs, and I need this particular profile. Right now, it's not standardized. What we understand, being part of the industry, both from the system company point of view as well as from processor company point of view, as mentioned, our other chairperson is from a system company. So based on our experience and based on the members' participation, we realize that this is not a standard process right now, and we want to fix that so that in the industry it becomes a standard norm. So that's what it will achieve at the end of it. That's the working group. We think that once we achieve our goal, it will facilitate that in the industry, and it will become a standard, just like it used to be that how many MIPS you need, or what is a core mark you need, or many standards have been done already which help this process or RFQ and make a playing field for all the SoC vendors. Now, moving along, these are some next steps that we come up with. These are not finalized, but once we achieve our goal, the number one goal that I mentioned just now, the second question is, how do we make sure that, how do we assign the profiles? whether it is just we publish whether we leave our charter to publishing the profiles and then every vendor is just going to claim, is that the charter? Or one charter could be that we as a working group, we work with some independent association, it could be embassy, to facilitate the certification of SoCs to particular virtualization grade. It could be that we look at there are many ways to do that. We have in the working group expertise to do that, because we are, as one of the speakers is the processor architect, and a lot of members are from processor companies, so we have expertise. And in fact, as in this webinar is to seek more participation so that many experts can contribute to this effort. Or second thing, or in order to do that, we will need some HRMs or data sheet. We want to form a technical committee which will evaluate that and then grade it. On the other side, we have argued that because it's a public committee, there are a lot of proprietary stuff, a lot of innovative stuff. Not every vendor would be willing to share their details, so it might defeat the whole purpose. So in order to do that, we might even, in order to circumvent that, we might even work with, again example is embassy, to develop some benchmarks targeted for different profiles or different market that will test those features at black box level and then come up with a mark, like it could be virtualization for networking mark, or it could be for storage mark, and so on. It's not defined yet, but those benchmarks which will help us to validate the feature capabilities and the performance, and based on the results we can say that this SoC belongs to this profile, or if it does, even though vendor claims it does, we will say this is the mark, this is the level of that, how many features it has added. So that's our next step, and based on our experience, as same members are part of embassy or other association, we think we can achieve that. But we need more participation from both processor vendors as well as from the system companies. And not to forget, equally important is the third piece, which is a hypervisor or the software companies, which needs to provide the environment to harness the capabilities of the hardware for virtualization. So that's, in nutshell, is the working group's charter. Now, as I said in the beginning, I'm gonna now hand over to another presenter, Brian Chin. He's going to share what are our thoughts and current progress on the second charter, which is multi-core virtualization profiles. Brian?
Okay, thanks, Rajan. Just a quick bit of housekeeping. If you have any questions or you need to provide immediate feedback, just type it into the little window on your screen, and we can see it. I'll try to address it as I'm talking. Or at the end, we're going to have a Q&A, and we can just open it up to some interactive discussion, texting and voice. So I'm going to, like Rajan said, I'm going to go over some of the ideas we've been thinking about for kind of this taxonomy of how you would classify different virtualization features. This is more of a straw man, some ideas here. It's not complete, so please don't take it in that vein, but hopefully they'll stimulate some thought as to what features might be important to yourselves, or what features we might be missing, or perhaps perhaps we're on the mark as far as you're concerned. So to start off the discussion, I just wanted to show an example of the kinds of things we see in desktops and servers, for example, provided by the primary providers by AMD and Intel today. There is no, quote, standard, but because they're the de facto standards in x86 land, they basically implement the same features, and these are features that we may or may not see in the embedded world. For example, they both have nested page tables to provide virtual addressing to guest physical addressing to host physical addresses. And they do it through TLB and nested page table structures that are in the memory, and a hardware page table walker. In addition, so they've done things like added IOMUs, ILTLB, so that PCI can come in, for example, with guest physical addresses, and these can be mapped to host physical addresses, providing a level of abstraction for the guest and kind of minimizing the overhead that the hypervisor has to provide. And I didn't put it on the slide here, but there's a bunch of work that both companies had to do to virtualize the instruction sets by making certain operations privileged so that the hypervisor could do the right thing under the hood. And that was something that both vendors have basically standardized upon, and you can run operating systems from AMD and Intel pretty much on most of the major platforms. Okay, so how does that apply to us? Let's see. Why is it? There we go. So application classes, we're thinking about broad categories here, and again, it's not a complete list. But if you think at the top, we've got general purpose computing, both enterprise servers, desktop computers, cloud computing today is a really hot topic, and that's right now dominated by x86. But certainly we're seeing a lot of interest in other architectures recently. So some standardization is probably required there, although a lot of that is already a de facto standard, right, in terms of what exists today in x86. But then we move on to like high-end embedded applications, the kinds of things where Cavium, for example, plays. We built silicon for. In high-end embedded, we've got applications like network and communications, both wireline SoCs like our Octeon product and wireless SoCs. We're also traditionally been in places like storage, which Rajan mentioned, and imaging, like in printers. And this is an area where there really aren't any standards for what virtualization means. Another market, very high volume, very important market, is consumer market, right, with portable devices, your smartphones and perhaps tablets. Also looking at non-portable devices like set-top boxes, home gateways, devices such as that, where the standards aren't really there in terms of what virtualization support means. Okay, so we just listed a bunch of features. Okay, what are the kinds of features that you might want to classify? Well, memory management's a big one, right? So it can be something very simple, right? In some machines and embedded applications, you might just partition the memory and use paravirtual addressing, where the guest is actually going to be changed to use addresses that are compatible with other guests. Or you might do some kind of block translation schemes where you're going to assign a range of addresses to each guest, and there'll be based and bound protections to prevent one guest from clobbering another guest. And finally, you might do things like nested page tables, which we borrow from the server and desktop world, where the hypervisor has its own set of mappings between guest physical address and host physical address that's managed completely invisible to the guest, so the guest can run unmodified. And of course, you need a certain amount of hardware support to make that go fast. And finally, how does this memory management fit in with I/O addresses? Are I/O devices going to be able to be programmed directly by the guest so that there's minimal hypervisor intervention by providing some kind of IOTLB or IOMMU? Or are you going to use paravirtualization techniques, custom drivers to allow guests to cooperate in the I/O space? How do you maintain quality of service between different guests? These kinds of features need to be spelled out so that vendors can design to a particular expectation in terms of what the system designer or customer expects. We also have the whole raft of issues with I/O, and in embedded there's a lot more I/O to think about than traditional server, where you have a network and disk and maybe a graphics card. So PCI Express SRLV is certainly an important standard, and so it'd be interesting to have in the standard whether that's supported or not in a particular profile. We've also seen a lot of customers do things like I hate this word, but it's physicalization, which is kind of subverting to some extent PCI Express SRLV by duplicating interfaces, making them appear physical when actually they're virtual. As part of the PCI Express spec, there's a scheme for address translation caches. Again, that can be a feature that can be either included or not included. We have to decide what the standard should be for different applications. And interrupts are important, right? Do interrupts get sent to the hypervisor where they're doled out to the guests, or are they allowed to go directly to the guests? And what are the implications for doing that in a multi-core processor in terms of interference between guests or quality of service? Rajan mentioned one of the things that distinguishes some of the embedded features that we see from the desktop and server spaces. We have a lot of co-processors. So a lot of these SoCs will have various custom packet processing blocks, or maybe a compression engine, an engine that does regular expression searching, or like in our chips we have all these, a crypto block. All these need to have some level of virtualization support, and that needs to be defined. The last area that I wanted to highlight was what's the performance, and this one is more of a philosophical issue in terms of what the chip is designed for. So we've been thinking about two axes here. One is kind of a scale-up focus, and the other is scale-out. Scale-up refers to building a processor that has a lot of capacity for compute, and it services a lot of guests who do not need the entire capacity of the chip. A good example is what happens in like server virtualization, where one of the primary motivations for going to server virtualization was that system vendors, or rather customers, realized that their servers were being underutilized. So a particular operating system might be taking 15% or 20% of CPU, and the CPU is sitting there burning a lot of power and costing a lot of money without being utilized. So the scale-up focus says, okay, well, let's take a bunch of guests and let's multiplex them on top of that server to bring its utilization up, right? So scale-up is focused on having hardware that is kind of over-capable for a particular guest and optimizing it by multiplexing multiple guests on top of it. So you have to do things like make sure that the guest context switches are fast, so that you can move between one guest and another and not waste a lot of time in the hypervisor. Scale-out focus is different. The scale-out focus says, well, look at the part, for example, like a Cavium Octeon today that we sell. It's, let's say, got 32 cores, and each of those cores is already close to 100% utilization when the traffic is flowing through it and the customer is doing their embedded processing. So it wouldn't make sense for that processor to optimize virtual machine context switch, because the CPU, each core is almost 100% utilized already. You don't want to actually add more virtual machines to it. But you still want to provide support for virtual machines, but you want to do it in a scale-out way, so that perhaps you have one virtual machine per core, and you can add more cores to get more virtual machines. Okay, so in the next slide. So here's just an example to kind of tie together the things we've been talking about. And again, it's just an example, it's not complete, but just to give you a flavor for what we're thinking of. So in the columns I've identified, let's say, 3 different markets. So for example, let's say the consumer market. If you're saying you're selling a processor into the consumer market, we would like to have a standard where you would, for example, you support some kind of memory protection scheme, either nested page tables or some kind of simple memory protection scheme like the base and bounds we mentioned before. For that market, maybe I/O address translation is not required. PCI Express may not be required, because like the set-top box may not even have PCI Express on it. Maybe you don't care about interrupt latency as much, so interrupts directly to guests is not an issue. And it can either be scale-up virtualized or scale-out virtualized, depending on how fast your processor is and your particular system architecture. In high-end embedded, we might say, oh, well, okay, to fit that profile, you have to support nested page tables, because being able to run guests unmodified is really important. You have to support I/O address translation, because the drivers need to run unmodified. You have to support PCI Express SRLV, so you can plug in different accelerators into your embedded application, and interrupts to guests for low latency. And in this particular case, we just said, let's say it was scale-out virtualized focus. So the cores are almost 100% utilized. You don't expect to be multiplexing on many guests on the core. But but instead you're going to have the cores scale out, add more cores for more performance. And just to contrast, I put general purpose computing, which is a server and desktop, and that profile kind of exists today, right? Those machines support nested page tables. They support IO address translation through ILTLB or ILMU. They support SRILV through their various south bridges and some now directly on the processor. Interrupts to guests could be optional. They have different ways of doing that actually today. And the focus seems to be on scale-up virtualization, where the cores are pretty powerful and you can multiplex multiple guests, on one core to bring up the utilization. Okay, so that is all I had for today. I think we have some time for some questions.
Hey, thank you guys. It looks like we've managed to keep everybody awake or so. One of the first questions, obviously I can't mention it's from a system company, and their question is, as a system developer, what is the value, or is there a value for us to be involved in this effort? Or should we just wait until it's done and then just check it out? Ryan or Rajan, take that question?
Yeah, I can take that. We definitely need input from system companies. This should not be, in my view, this effort should not be driven by any one particular type of company. We need to understand the requirements from the system vendors. We need to understand, have input from software vendors and also from the SoC providers, because ultimately we don't want to make a solution, speaking from a chip vendor standpoint, we don't want to make a solution that is not going to address the market need. Right? So we definitely value system input.
So maybe, Surinder, if you're on the line here, you could tackle that question as well, since you are a system developer, how you see benefit in working with this. Okay.
Surinder, are you mute?
Yeah. No, we can't hear you. Okay, well, you seem to be having technical difficulty over there. So
Marcus, this is Rajan. Just to add to what Brian said, so it's a so fragmented market, the networking or I would say multi-core, that different markets have different needs in terms of the virtualization hooks or virtualization solution for whether it's a networking or storage or wireless, or it could be printing or media or whatever. So that's why we definitely need more participation from the service system companies, so that they can bring to the table their market needs and what is more important, what kind of profiles or what kind of hardware hooks are more important for them. So that's why it cannot be just a one, partly from first of all standardization point of view, and more that is one aspect, but also from the problem definition itself. Technically, we need to have participation from different system companies as well to facilitate that.
Yeah. So I have another question that came in here, and I'll just kind of rephrase it a little bit. And basically they're asking that since you guys are representing the networking or the telecom communications sector, the thought is that this is mostly focused for that market, but do you see how this might be applicable for other markets like the mobile space, where virtualization is definitely becoming a critical element?
Yeah, I'll take that one, Brian. I think that it's definitely true that being Cavium, we're addressing, or the talk, we mostly focus on networking, but the general scheme we're applying here can be, this taxonomy can be applied to most any embedded application, and we definitely want to have profiles for consumer and different kinds of applications that we didn't even list here. So that's one of the reasons for getting more participation from other companies to get a different view of what the requirements might be in the different application spaces.
Okay, so, sounds reasonable. Again, anybody else out there with some more questions, keep plugging them in, and we'll take them as they come in.
Marcus, can you guys hear me now?
Yes, we can. So,
okay. I had some. Yeah, I think I finally got to the problem here. Yeah, sorry about that.
So if you want to step back and add a little bit to what Rajan and Brian had said about the system developer's perspective, feel free.
Yeah, so as all of us know that there's a proliferation of multi-core SoC devices. And in this context, it's not just the CPU resources. You have accelerators, crypto, regex, compression, and there are other packet processing blocks within an SoC, like, for example, a buffer pool allocator or a timer block. So how do you partition the resources and use it efficiently? So that's where virtualization comes in. And there are many use cases, where we which is well known, and where you definitely need to use virtualization. One thing which Rajan was talking about was using the user plane and control plane processing on the same processor. Like that, you got in a telecom space, in-service upgrade, where you can run the new version of the software in a separate VM and synchronize all the states with the old version, and it becomes active. So virtualization would make it very easy to do something like an in-service upgrade. And apart from that, you could also have dynamically load balance the cores and processes, for example, between the control plane and user plane. At different points of time, you have, for example, in the night time you run billing services, so you have more control plane load, and in some of the times during the day you have more user plane load. In that case, you could dynamically load balance between the user plane and control plane and use your CPU resources more efficiently. And like that, you got you can separate even the platform and application software. There are a lot of use cases where, from the system perspective, we see that virtualization is going to be very useful, and these problems have to be, in the embedded space. We need to have solutions for those.
Okay, thank you very much. And one other question has just come on. It's basically asking, what is the current status of the virtualization hooks in SoCs? So any of you guys, if you want to address that, feel free.
Yeah, I will take that, Marcus. Thanks. So as I said in the beginning of the talk, it's more fragmented, or it's not very consistent that one can say that this has been done or this has not been done. So every vendor has different their own solutions, be it from the hardware paging or that Brian was mentioning, or it could be from I/O virtualization, or from hardware acceleration virtualization, or even from cache or memory virtualization. So every vendor has their own solution, and because of that, no particular OS or no single OS or no single low-level drivers could standardize that will, once you have written for one vendor, it could work for another vendor. So it is more it's more proprietary solutions. There have been efforts to standardize, let's say, across MIPS or across ARM, but not all MIPS vendors are implementing them as it is or adhering to that. So that's why that has caused a problem, because if one OS is written for one particular feature, doesn't mean that the same OS be it Linux, could take advantage of the similar feature or in the similar look and feel on a different processor vendor. So that's the issue in current market that we want to address, that we should have some standardized hooks on the SoCs in the embedded market as well, which in the x86 or server market, x86 being the only vendor, you can think of that has become a de facto standard, and they have done pretty good job in publishing their hooks or all the hardware things and in the public domain, as well as educating people. And Intel having more resources both in software as well as in hardware, they can spend on that. Here, first of all the members they don't have that many resources, so we have to have a collective effort in the industry to come up with something standard so that everybody can use it. Ultimately, it's going to benefit the software vendors, it's going to benefit the system companies, as well as clear up the confusion on the processor vendors, so that we don't have to have proprietary hooks with the worry that ultimately we have to change it to standardize to some other thing. So it's going to help all the three stakeholders with this app.
Okay, thank you very much. And before we, actually one more question's just come in here. So what is the timeline for getting a standard drafted?
Yes, I'll take that. So we are planning to finish the first round of discussions as well as deliberation within the members in this Q1, and by Q2 2012 we would that's our goal, to have the final draft ready and accepted by the system companies and processor companies. So in this quarter, and that's why this webinar is very timely, that we want to open up for the people, so that they can give their inputs and contribute to the effort and help us in defining it. So that all that process we want to do it in this quarter, where we get different inputs and work together, and then in next quarter we will finalize and work on the defining it, and then getting acceptance from the different both the parties, as I said, system companies as well as from the actually all three parties, not only system companies and processor, but also from the software like the hypervisor or the OS companies, so that they also agree with the hardware hooks we are adding in terms of look at.
Okay. So obviously one of the main goals of presenting today was to convince you to join this consortium and participate in this working group. And along with the MCA Virtualization Working Group, we also have several other active working groups that as a member you're able to participate in. And I'm sure if you're on this webinar today, you've probably already been to the website, so you can, you've probably already reviewed them. But if you have any questions, feel free to email Surinder or Rajan or myself directly. We're happy to help you, and we'd love to see you participating in this effort, because obviously the more inputs we have, the more reflective of the real world it's going to be. So I'd like to thank you all for joining us here today, and this webinar will be posted live. You'll be able to, or not live, but it'll be posted up to our website, so you can download and listen to it again and check out the slides. So thanks once again to our presenters and to all of you for being here with us today.
Thank you. Thank you, Marcus, for hosting it.
Thank you.